Today we continue to talk about shortest paths. Last week we talked about breadth search algorithm and Dijkstra algorithm, and these two algorithms were used for shortest path problem when all weights are non-negative. And today we'll talk about how to solve this problem if you have negative edges. So if you have all weights are non-negative, you will just use the Dijkstra algorithm. And if you have negative weights, then you kind of need to use another algorithm. Let's see. First, yes, the source is 720 because I have different setup today because I forgot my streaming laptop in ITMO. So today I'm streaming from my MacBook Air and it's not supposed to stream anything. So I just hope it will handle this lecture. Okay. I believe it should be fine. Okay. 720 should be enough. Yeah, looks fine. I'll try not to draw any small pictures today. Okay, so first, if you have negative weights, the first problem you can get is that you may have negative cycles. So, for example, you may have a graph like this, and you'll have something like this. And this is S, and the weights are, let's say, -5, -10, 3, let's do, and 3, and let's say 4 here. So what's the problem in this graph? In this graph, the problem is that you have a negative cycle here. So here you have this cycle, and the sum of weights on this cycle is negative. Why is this a problem? Because if you have a negative cycle, then the shortest path cannot be defined. Because if you move along this cycle, the cost of your cycle will decrease, and the more turns you have around the cycle, the smaller your cost is. So, if you try to move from here to here, you can just use this h -5, or you can use this h plus this cycle. So the length of your cycle will be -5 plus -10 plus -5. Yeah. So length of the cycle is -5. So you can use this path, and the length will be -5. Or you can go here and then use this cycle. So the total length will be -10. If you use the cycle twice, the length will be -15, and so on. So you can make the length of your path as small as you need. So there is no shortest path. For any path, there is another path which is shorter than your path. So if you have a negative path, negative cycle, then the problem is not defined. Because if you take some path from S to T, and you have a negative cycle here, then there is no minimal path. So for any path, there is another path which is smaller than your path. That's a problem. But maybe you can solve one problem. Maybe if we just forbid to use cycles. So let's say we want to find a shortest path, shortest simple path. So we want to write shortest path, and we just forbid to use the same vertex twice. Yeah. So let's say we want to find the shortest path from S to T, which doesn't contain any cycles. Can you solve this problem? What do you think? So if you have the following problem, you have some graph with negative cycles, and you want to find the shortest path from S to T, which doesn't contain any cycles. What do you think? Can you solve this problem or not? I just remind you, you need to say something in the chat, especially when I ask something. If you don't know, just say I don't know. If you say everything is clear, say everything is clear, okay? I don't know. That's an answer. Problem is you can't find this. You can't solve this problem. This problem isn't P-complete. Why this problem isn't P-complete? Because if you can solve this problem, if you can find the shortest simple path, then you can find a Hamiltonian path. Because let's say you have a graph and you want to find the Hamiltonian path in this graph. So you want to find the path which visits each vertex exactly once. Then we can you have some graph again. You have some graph. Let's see direct the graph. And you want to find the Hamiltonian path in this graph. So what you can do? You can assign, let's say, weights -1 to all the edges of this graph. And now in this graph, you want to find the shortest simple path. So if you find the shortest simple path, the length of this path will be the number of edges you visit. And you want to maximize this number. So what you want to do, if you want to find the shortest simple path, you will actually find the longest simple path. Yes, you will find the simple path which contains the maximal possible number of edges. And it is equivalent to finding the Hamiltonian path. So if you have a path which contains n-1 edges, then this path, if you have simple path of n-1 edges, this is the Hamiltonian path. So if you can find the shortest simple path, then you can solve a Hamiltonian path problem. And the Hamiltonian path problem isn't P-complete. So this problem is also in P-complete. That's the problem. So if you have a negative cycle, then you can find shortest path because there is no shortest path. And you can find a shortest simple path because it is a P-complete problem. So in both cases you have problems. So we will, what we'll do, we'll just forbid any negative cycles. So we will allow edges to have negative weights, but for any cycle, the sum of weights on this cycle will be non-negative. So that's how the problem will be defined. So you have a graph. Each edge has some weight, and for each cycle, the sum of weights of all edges on this cycle is non-negative. Let's say here, for example, let's say this is -1. So if this weight is -1, then the weight of this cycle is actually non-negative. So it is -1 plus 1 plus 3, it's 4, right? And it is the only cycle. You mean P-Harbs is no? You can make a yes-no problem from this problem. No, you can say something like, is there a path which has length at least x? So something like this. So, if you really want to make it in a form which is allowed in B class, so it is in B class. Yes, we have usually yes-no problems. So if you want actually to make an NP problem, NP-complete problem here, so you will say that something like, so you need to make yes-no problem, yes. So you want to make a problem like, is there a path from here to here which has length at most x? And it will be yes-no problem. And this problem isn't P-complete. That's more accurate way to do it. It doesn't matter usually. Now, if we forbid negative cycles, then the problem is always defined, because each shortest path is a simple path. If you have a shortest path from S to T, which contains some cycle, you can remove this cycle from this path, and since the weight of this cycle is non-negative, the total length of your path will be not increasing. So you can remove this path or this cycle. and have a shorter path. Yeah? So now the problem is defined because there is always a minimal path. Because the path is simple, there is a limited number of simple paths from S to T, like at most n factorial paths. Yeah. So there is some fixed number of paths from S to T, and from fixed set there is always some minimal path. So the problem is always defined. So even if you have negative edges, but you don't have any negative cycles, there is always a shortest path from S to T. Yeah. Okay. Let's go. Now, how to find the shortest paths? There is a simple algorithm which is called Bellman-Ford algorithm. In Russian, it's usually Ford Bellman, but in English literature is usually Bellman-Ford. I think it's because of alphabetical order. I'm not sure why. In Russian, usually it's called Ford-Bellman, but I'm not sure why. Bellman. I believe it's one N for the algorithm. Check the spelling again. Yeah. So how this algorithm works? This algorithm is actually a simple dynamic programming algorithm. Actually, Bellman was one of the founder of this dynamic programming method. So one of the first problem which was solved by dynamic programming. So how to use dynamic programming here? We know that this path is a simple path. So the number of edges in this path will be limited to n-1. So the number of edges in the shortest path from S to T is at most n-1. So let's try to make a dynamic programming by the number of edges in the shortest path from S to T. What we'll do? We'll say, for example, let's say d vk will be the shortest path. No, the length of the shortest path, yeah? From S to T, from S to V, which contain no more than k edges. That's all. That's the plan. And now we'll calculate these values by increasing of the value of k. So first we'll calculate for k equal to 0, then for k equal to 1, and so on. In the end, when k will be equal to n-1, we will find the shortest path. Since the shortest path always contain no more than n-1 edges. Okay, how to calculate these values? Well, let's remember how dynamic programming works. First, when you make a dynamic programming, you need to make some starting values. Okay? So, for example, here, if k equal to 0, dv0. So it will be the first layer of your dynamic programming. So like some starting values of your dynamic programming. Yeah. Do you remember how dynamic programming works? Yeah. So if k equal to 0, then you need to find shortest path from S to V, which contains 0 edges. There are not so many paths which contain 0 edges. Actually, there's only one path with empty path. Yeah. So the only path which contains 0 edges is this like empty path from S to itself. So distance to V, if you use no more than 0 edges, will be 0 if V equal to S, and plus infinity if V not equal to S. Why didn't consider edge simple paths? You can consider edge simple paths. What's the problem? No, I claim that the shortest path is always vertex simple. So for any shortest path, any shortest path can contain the same vertex twice. So if in your shortest path you have some vertex twice, you have vertex v, and then again you have vertex v, then you can remove this part, because this part is a cycle, and the weight of any cycle is non-negative. So if you contain some vertex twice, you can remove this part from your cycle or from your path, and the total length of your path will be decreased. Yeah? So your shortest path shouldn't contain the same vertex twice. And since all the middle vertices here are different, the total number of edges will be at most n-1. Yeah, right. Now, so what we'll do here, we'll calculate, okay, this is the first layer of your dynamic programming. So if k equal to 0, then distance to each vertex will be 0 if for vertex s, and plus infinity for other vertex. So this plus infinity is just its shortest path, but since there is no path, yeah, so it's minimum of an empty set. So minimum of empty set, let's set it to plus infinity, yeah, like usual. So it's kind of makes sense, right? So it's like neutral element for the minimum function, yeah. When we have negative cycle, why don't we try to solve the problem of edge simple shortest path? Edge shortest simple path. Edge simple shortest path. Let me think. I'm not sure if this problem is solvable or not. So if you consider only edge simple shortest paths from S to T, is this problem be complete or not? I'm not sure about this. I'm not sure. It's not trivial. Maybe it's even solvable. Let me think about it. We'll talk about it next time, okay? That's interesting. It looks kind of like solvable problem. But maybe for some reason it is also incomplete. I'm not sure. So let's go back. So we start dynamic programming with value k equal to 0. Now we need to make transition from k to k plus 1. No, let's do it from k minus 1 to k. So I want to calculate this value. I want to find the shortest path from vertex s. From vertex s to vertex v, and this path should contain no more than k edges. So let's look on this path. So this is some path from s to v. If this path contains less than k edges, less than k edges. If this path contains less than k edges, then it actually contains no more than k minus 1 edges. So the shortest path from S to V, which contains less than k edges, is actually dvk minus 1. Right? Second case, if it contains exactly k edges, then let's look on the previous vertex in this path. So we have some shortest path from S to V. Let's find this node. So there is some previous node in this path. So there is some path from S to V, and this closest node to V is U. So this last edge in this path will be from U to V. So let's iterate for all possible edges. So let's iterate for all edges which go in to node V. Now, if we want to find shortest path which have node U here, then this part will contain k minus 1 edges, right? So what we need to do, we need to find shortest path from S to U which contain no more than k minus 1 edges, plus this one edge. And among all of these possible cases, we need to find the minimal one. Yeah? So we need to find minimum of all values. So we go to vertex u using k minus 1 edge, plus we need weight of this edge uv. That's all how you calculate the shortest path. So again, the shortest path from S to V, which contain no more than k edges, will be either shortest path of length at most k minus 1, or some shortest path from S to U of length at most k minus 1 plus one edge. We will iterate over this edge, and now take the minimum of all these values. That's the whole plan. Let's write the code. The code is actually very simple. So first we say that ds0 is 0, dv0 is plus infinity for all v not equal to 0, not to s. And now we iterate over all values of k. And just implement this formula. So we iterate over all vertices. And for each vertex, we take minimum of these values. Let's say like this. Let's say dv k equal to dv minus 1. So use this, and now we iterate over all edges. For all edges uv, we implement this minimum. uk minus 1 plus weight like this. Cool. That's basically the whole algorithm. So that's the whole Bellman-Ford algorithm. Let's talk about time complexity. What's the time complexity of this algorithm? Well, time complexity is calculated very simple. We just have these three for loops. So here we have n iteration of this loop, and here what we do, we iterate over all vertices. For each vertex, we iterate over all edges going into this vertex. So these two for loops combined make at most m iterations. So total time complexity will be that's much worse than for Dijkstra algorithm. For Dijkstra algorithm, we have something like m log n operations. Here we have nm operations. So this algorithm is significantly slower than Dijkstra algorithm, but it can work when you have a negative edges. And that's kind of all. That's all we can do actually. We will modify it a little bit, but we will not improve this time complexity actually. Again, you forgot to say something in the chat. When the chat is quiet, I think that something is broken. And I just continue to check that my stream is working. So just say something at least every minute, okay? Now, what we'll do next? We will try to improve this algorithm a little bit. First, let's solve this example first. So we have this graph, since I have the graph. Let's just show how this algorithm works in this graph. So we have this graph. We have 4 nodes. So the length will be, so let's say k, will be from 0 to 3. I can count. And so this is ready. Let's put some numbers here. So first, when k equal to 0, then we have 0 for vertex S and plus infinity for all other ones. Now we move to k equal to 1. Let's look on the vertex 1. For vertex 1, we have no incoming edges, so the length is still 0. For vertex 2, we have ingoing edge from node 4, but the distance to node 4 is plus infinity, so the sum will be infinity plus 2, it's still infinity, so it doesn't matter. And we have ingoing edge from vertex 1. So from vertex 1 to vertex 2, we can use this edge, so the total length will be 0 plus 4, it is 4. For vertex 3, we have two ingoing edge, from here and from here. So from here we will have distance minus 5, from here we have distance infinity. So minimal is minus 5. For vertex 4, we have ingoing edge from 3. Distance to node 3 is infinity, so it will be infinity minus 1 and still infinity. Okay, I'll think about this problem later, okay? Not now. Let me finish this first. Now, for k equal to 2, so we have 0 here. For vertex 2, again, we have 4 from here, or infinity from here, because still here we still have infinity, so we have 4 here. Vertex 3, we still have 5, minus 5, or 4 plus 3, it will be 7. So 7 is more than minus 5, so it will be 7, minus 5. It will be minus 5. And for vertex 4, it will be minus 5, minus 1, it will be minus 6. And finally, when k equal to 3, we have 0 here. For vertex 2, now we have this edge going from node 4. It will be minus 6 plus 2, so it will be minus 4. Minus 4 is less than 4, so it will be minus 4 here, minus 5 here, and minus 6 here. And that's the final answer. So these are the distances to all the nodes. Now, let's try to improve this algorithm a little bit. What would be the improvement? First, let's improve the memory. Look, right now, we use this big two-dimensional array. So the size of this matrix is n multiplied by n. So we have n square matrix. But we actually don't need this square matrix. So in this square matrix, we only use 2 rows. So first we build the row 0, then we build the row 1 using row 0, then we build the second row using first row, then we build the third row using the second row, and so on. So each time, so what's happening? First you have only row 0, then using row 0 you build row 1, yeah? Then you use this row 1 to build row 2, and so on. So each time you need only the previous row. When you construct row k, you only need the row k minus 1. You don't need all the previous rows. So what you can do is to store in your matrix only last 2 rows. So you use row k minus 1. All the rows above k minus 1, you don't need them anymore. So you can forget all the rows here and only use these 2 rows. So if you do it like this, the memory complexity will be not n squared. So the memory will be improved to linear. Well, that's a common trick for dynamic programming, actually. So if you have this two-dimensional array and you only use last few rows of your array, so you can forget all the previous rows of your array and only use these rows. So if you do it like this, you will improve the memory to linear. Okay. Now, another nice improvement. You can actually make it even simple. So instead of having 2 rows, you can have only 1 row. So you can use only single one-dimensional array for the whole problem. Let's do it like this. I'll just modify this code. Okay, I'll not erase this one, but I'll make another one here. Okay, the idea. Let's make one single one-dimensional array. So let's say array D. First, we'll say that d of s equal to 0, and d of all other nodes will be plus infinity. Plus infinity. Plus. For all nodes not equal to s. And then we'll just make this k-1 iteration and -1 iterations. Okay, 1, 2, and -1. And here we'll do the same thing, but we'll use the same array here. So we'll recalculate value for node v using value for node u. But we'll use value for node u not in previous row, but in this row. So what we need to do, let's write it like this. We'll iterate over all edges. So let's iterate over all edges in our graph. And just implement this relaxation. So we'll say dv will be minimum of dv and du plus weight of edge uv. That's all, that's the whole algorithm. I claim that this algorithm is also correct. So this algorithm will give you, in the end, the value of dv will be the distance from S to V. Let's prove this. Why this algorithm is also correct? No, because it kind of uses the same invariant as this algorithm, but slightly modified. So what will be the value of d? So first observation, the value of d is always the length of some path. So first observation. So dv is always some path of some path. Let's prove this. Look, here we have shortest path here of length 0, and we have some, no, if it is plus infinity, there is no path, yeah? So there is some non-existing path of length plus infinity, yeah? And what we do here we assign value du plus the weight of this edge to this dv. So the length of dv will be du plus the length of this edge. So if we have some path to du, we can add this edge to this path. So this sum will be the length of some path from S to V. Okay? So we have some path from S to U plus this edge. So this sum is some path from S to V. So these dv are always correct. So there is some path of this length. And now the second observation, that dv is not larger than length of the shortest path of at most k edges. Shortest path of at most k edges. So after every iteration, we will build some paths in this graph. So this dv will be length of some path, and this path will be not worse than the length of the shortest path of k edges. Well, let's prove this. Well, again, on iteration 0 it's correct. In each next iteration, here we will iterate all edges to node V. So for node V, so for node V, we iterate all ingoing edges. So if there is a path of at most k edges from S to V, there is a path from S to U which contain no more than k minus 1 edges, right? So we will iterate through all edges, so we will find this edge. For this edge, we will find some path from S to U which is not worse than this path. And we will add to this path this edge, so our path here will be not worse than the shortest path of at most k edges. Again, there is some path, some shortest path of at most k edges. Let's find this path. If we have this path, there is another path from S to U of at most k minus 1 edges. Here we will find this edge UV, and we will apply this minimum. So for value for our vertex V will be not greater than length of some path from S to U, which is not worse than the shortest path of k minus 1 edge plus this edge, so it will be not worse than shortest path from S to V of at most k edges. That's the plan. Go. That's all. Cool. Again, let's try to apply this algorithm to this graph. So what will be going on here? So we have this already. It is initialized like this. And now we just iterate over all edges in our graph and try to apply this operation. So we iterate over all edges in arbitrary order and just apply this operation. So we try to, it's called relaxation, doesn't matter. So we will try to update the value of distance to node V using distance to node U, something like this. So let's iterate all the edges in graph in some order, doesn't matter. So let's, for example, let's pick this edge. So we pick this edge. I will mark edges which I always do. So let's pick this edge. For this edge, we update value of node 3 using node 1. So the value was minus infinity, but now we use this edge, so this value will be minus 5. Now let's pick, for example, this edge. So we pick this edge. So we update value for node 4 using value for node 3. So it will be minus 5, and this will be minus 6. Now let's pick this edge. For this edge, the value here will be updated to infinity, so it will not update. Now let's take this edge. So we update value for node 2 as 4, right? So it will be 4. And now we pick this edge. So update value here as minus 6 plus 2, it will be minus 4. And now this is just the first iteration. So in the first iteration of this loop, we will update the array like this. And now we apply the second time. So we try to apply the same loop 3 times, because the length of the short path will contain no more than 3 edges. So we'll apply the same loop 3 times. Well, let's apply it again. So again, we try to relax this edge. So if we relax this edge, then here will be at most minus 5. It's still minus 5. Length here will be minus 6. It is minus 6. Try to relax this edge. Here will be minimum of minus 4 and 4. It will be minus 4. And try to relax this edge. It will be at minus 4. So we try to relax all the edges, and none of the values changed. So after the second iteration, all the distances in array are the same. What does it mean? It means that these values will no longer be changed in all future iterations. So if we at some iteration, if we apply this loop and all the values in array D didn't change, it means we have the final values of array D, because on all other iterations they also still will have, because we have the same values in array D. If all these values didn't change in one iteration, they will not change in all future iterations. Cool. That's all. Now, you see here, in this example, we were very lucky. Yeah, we were lucky because on the first iteration, we find all the correct values of these distances. It actually depends on the order in which we apply this operation. So we apply this operation in this order and we got all the correct values. If we try to iterate over all edges in different order, we can have something like this. Let's say that we have infinity, infinity, infinity. Again, let's try to do it again, but we'll apply this operation in different order. So for example, let's start from here. So we apply this edge first, say this is true. Then let's say apply this edge, so it will here the value will be 7. Then let's say apply this edge. 7 minus 1, 6. Arithmetic system. Okay, now we apply, for example, this edge. So here it will be minimum of, no, it will be minimum of, why it is 2? Why is it 2? Must be 4, right? Now I apply this edge, so distance to here will be minimum of 4 and 6 plus 2, 8. So the distance is still 4. And now we apply it to this edge, so distance to 3 will be updated to minus 5. Again, we finish the first iteration, we apply this operation to all the edges of our graph. And the distances are not final yet. So we apply it the second time. So we will apply the operation at most n minus 1 times. We can prove that after n minus 1 iteration, we will have the correct distances. But it may happen that we have the correct distances even before n minus 1 iterations. So the number of iterations here is at most n minus 1, but it may happen that we will have the correct values before the end of this loop. So what we can do? We can optimize it a little bit. We can do it like this. We can do these operations until we have a situation when no values of d changed. So we can do it like this. No, let's update it. So let's say, for example, let's say, okay, let's make a Boolean value, okay? And then while not okay, we will make this loop again. So we'll say, okay, equal to true. And now we iterate over all edges uv. See if the value is updated. So if distance to u plus edge uv is less than distance to v, then we update this distance. And say okay is false. Like this. So now, if OK is true, it means we didn't change any values in array D. If we didn't change any values in array D, it means all the values are correct. So we try to improve these distances, and we didn't prove anything. It means that we have the correct distances to all the nodes. That's all. What is the time complexity of this algorithm? Again, the worst case time complexity will still be nm. Why is it so? Because in worst case, we may have n minus 1 iterations here. So it is possible to have n minus 1 iterations here. So we have at most n minus 1 iterations here. And this loop is, again, iterated over all edges in the graph. So time complexity will be the same. But it may be better. So for some graphs, it may have small number of iterations. Well, let's see. Let's. Let's have a simple graph. Let's have a graph like this. So this is S. Like this. So this is the shortest path from S to T. Is it possible that we will find the shortest path in a single iteration of this algorithm? So let's take some graph. So in this graph you have this shortest path. So this is the shortest path. Is it possible that we arrange the edges in such an order that we will find this shortest path in a single iteration of this loop? Yes, if you arrange the edges from left to right and just apply this operation from left to right, then again you first apply this operation to this edge, and now you know the correct distance to this node. Then you apply operation to this edge, now you have correct distance to this node, and so on. So for any graph, there is a possibility that you arrange your edges in such an order so that you will calculate the correct distances here in a single iteration of this loop. But is there a possibility that you will run this loop n-1 times? So let's best, let's say, one iteration. Best. Let's find the worst case. Is it possible that we arrange our edges in some bad order, so this loop actually make n-1 iterations? If you just permute the nodes, no, if you do it in random order, we'll talk about random order in a minute. Let's find first. Let's talk not about random, but some very worst case. So what is the worst case for this algorithm? So if we have this shortest path from S to T, is it possible that we need n-1 iterations to find the shortest path? Oh. No, because here I claim that the number of iterations is at most n-1. I want to check that it's actually, maybe it's better, maybe we're just always lucky. Maybe there is no such case when you actually need n-1 iterations. Yes, if you apply this operation in reverse order, so if you apply these operations from right to left, so again, what will happen? So first, you have correct distance calculate only for the node S. Now you go from right to left. You apply this operation here. You don't change anything. You apply it here, you apply it here, you apply it here, you apply it here. Then you go here. Now you know the distance to this node. And that's all. The first iteration finishes. Now you make the second iteration. So again, you go from right to left. You apply here, 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 here. Oh, now you know the distance to here, and so on. So on each next iteration, you find the correct distance to only one node in this path. So you will need n-1 iterations. So there's actually a big gap here, so between best and worst case. Let's think about it. So if we just shuffle all the edges, maybe the random order is good. So what is the random order? So imagine here you just shuffle all the edges and apply this operation in random order. What will be the expected number of iterations? What do you think? Just try to guess. Maybe it will be good. Maybe it builds on log n. It would be great to have log n iterations on average. Yeah. Maybe it is square root of n. It will also be great. So if the average number of iterations is less than n, then the average time complexity will be less than nm. So it will be kind of great. Yeah, good guess. So actually, if you apply this operation in random order, actually the expected number of iterations will be about n over 2. Well, because on each iteration, you will find about 2 new distances. So again, so what will happen? You apply operation in some random order. Yeah. Well, first you will apply. You need to apply operation to this edge first. So when you apply operation to this edge, you need to apply it to this edge. So what is the probability that you apply this operation to second edge after you add it to the first edge? It's about 0.5, right? So about 50% probability that this edge will go after this edge. So there is about 50% probability that you will apply the next operation after the previous operation. So the probability that you will make a next step will be decreased exponentially. So every time you will make around 2 steps in this path. So after each iteration, you will find about 2 new distances in this path. So the total number of iterations here will be about n over 2. So it's still linear. So total time complexity again will be like this. So we didn't improve anything, but it is kind of nice exercise. Okay. Good. I think it's enough for Bellman. Let's move to Floyd algorithm. The next algorithm I want to discuss it's Floyd algorithm. It's called Floyd-Warshall usually. I know why there's all 2 people. I'm not sure why they always need 2 people to invent the algorithm. Let's see. So now we'll talk about Floyd-Warshall algorithm. Floyd, like this, right? So this algorithm solves a slightly different problem. So imagine you have a graph and you want to find distance between every pair of the nodes. So you want to construct something like this. You want to construct array VU will be distance from V to U. So for every pair of your of nodes in your graph, you want to find the shortest path from V to U. So in Bellman-Ford algorithm, we have this specific node S. So we want to find shortest path from S to all other nodes. In this algorithm, we all want to find a shortest path for all possible pairs of starting and ending nodes. Well, first, what you can do, you can just apply Bellman-Ford algorithm n times. Yeah. So you can just iterate over all nodes S, and apply Bellman-Ford algorithm for this starting node. Yeah. So you can just apply Bellman-Ford algorithm for all nodes V. The time complexity will be quite simple. We need to apply Bellman-Ford algorithm n times. Complexity of Bellman-Ford is nm, so total time complexity will be n square m. So the Warshall is the algorithm for transitive closure and the Floyd algorithm for shortest path. Makes sense. And they just combine these 2 algorithms in a single algorithm. Okay. Any lower confidence problem? I'm not sure. I believe that's the best we can do in this problem. I'm not sure if there's a lower bound for this problem. I kind of believe that's the best algorithm we know by now, but I'm not sure if it is proven that there's no better algorithm. It's an interesting question. I don't know. Now, let's go to Floyd-Warshall again. So, what we want to do, we want to calculate distance between every pair of the nodes. If we just apply Bellman-Ford algorithm n times, time complexity will be n square m. But what we can do, of course, we can improve this n complexity using a very simple dynamic programming algorithm. So, what is this? So very simple algorithm. We'll use dynamic programming again. In this dynamic programming, we'll make k iterations. So on iteration k, we will calculate the following values. We will say that value d of vu will be the shortest path from V to U, such that all the middle nodes in this path have indices at most k. Middle nodes. So that you have this node V, and you have some other nodes in this path. These nodes must have indices at most k. So here we have nodes from 1 to k. That's the whole plan. So now let's start. So if k equal to 0, so if k equals to 0, then we can't have any middle nodes in our path. Yeah? So if k equal to 0, then the only path we can get is the path of the single edge. Because if we have any middle node here, this node must have in this node more than 0. So if k equal to 0, k equals to 0, then distance from V to U will be just the weight of the edge from V to U. So this is the only path from V to U which doesn't contain any middle nodes. If there is no edge, it's plus infinity. Now, let's try to move from iteration k to iteration k plus 1. No, from iteration k minus 1 to iteration k. So we will move from k minus 1 to k. Let's see. We have this path from V to U. All the nodes here have indices at most k. Again, there are two cases. Case number 1. All the nodes here are strictly less than k. If all the nodes in here in this path have indices strictly less than k, then these indices have are less or equal to k minus 1. So we need to find the path from U to V such that all the middle edges have, all the middle vertices have indices at most k minus 1. And this is the value dVu from the previous iteration. iteration k minus 1. Second case, if we have, so we have values not greater than k, so if all values are less than k, then we have this. So now we need to get, if we have some node with index k, so we have this path, and in this path we have vertex k. So if we have vertex k in this path, then let's split this path into two halves. So let's look into this part and this part. All the middle nodes here are less or equal to k minus 1. And all the nodes here are less or equal to k minus 1. Yeah? Because all the nodes are less or equal to k, and we have k here. So all other nodes are not k. So they are less or equal to k, but not k. So they are less or equal to k minus 1. So now the distance from here to here will be the shortest path from v to k plus the shortest path from k to u, like this. That's all. That's the whole idea. Now we just apply this operation to all pairs of vertices, and we will have the correct values for the next iteration. Let's write like this. So we have iterations k from 1 to n, and now we iterate all pairs. Let's look at this. For v from 1 to n, for u from 1 to n. And here we just say that the distance between v and the u is the minimum of all distance. It's the first case, right? And this sum. That's all. That's the whole algorithm. That's the whole Floyd algorithm. So that's the whole code actually. No, you need to initialize your ID, but you can do it. What is time complexity here? Time complexity is very simple. So you have 3 loops. Each loop make exactly n iterations. So the total number of iterations of these 3 loops will be n squared. And cube. That's good. And cube. That's all. That's better than just applying Bellman-Ford n times, right? So here we have n squared m. Here we have n cube. So if the number of edges is large, so if this m may be up to n squared, right? So if your graph is very dense, then you have here you have n squared multiplied by n squared, you have n power 4, and here we have n cube. So it's definitely better, and it's actually pretty fast. So the constant factor is very small, since you have very simple operations here. So it's actually really fast algorithm for finding shortest paths. Very nice algorithm. And again, this algorithm can be applied even if you have negative edges, since we don't have any problems here of negative edges. We never assume that the weights of edges are non-negative. So this algorithm can be applied even if you have negative edges. Nice. Now, what I forgot, I already erased it, but it doesn't matter. What if you have negative edges? So what happens if you have negative cycles? So what happens if your graph actually have negative cycles? So if your graph has negative cycles, you kind of want to detect it, right? So you want to find, you want at some point to figure out that your graph actually is bad. So if someone gives you a graph and asks you to find shortest path from here to here, and this graph actually contains some negative cycles, you kind of want something to detect this problem. Yeah, so you want to make some, yeah, I erased the Bellman-Ford algorithm. So you want to make some check on this algorithm, which checks that the graph actually contains negative cycles. Sorry. So how to do it? No, let's use this Floyd algorithm. Then we'll move back to Bellman-Ford. So in this Floyd algorithm, the way to detect negative cycle is the following. So if you have a negative cycle, then at some point you will have some node V such that the shortest path from V to itself will be less than 0. So at some point you will find this node K, and then in these two loops you will try to calculate the distance from V to itself. You will find this distance from V to K plus distance from K to V, and if this sum is non-negative, if this sum is negative, you will update value dVV. It will be less than 0. So the way to detect you have negative cycle in the Floyd algorithm is very simple. So after each iteration, you just need to check that on the diagonal of this matrix you have all zeros. If you have some value that is less than 0 on the diagonal of this matrix, it means you have a negative cycle. What happens with Bellman-Ford algorithm? So if you have Bellman-Ford algorithm, how to detect negative cycle in Bellman-Ford algorithm? In Bellman-Ford is actually where is this? What you do in Bellman-Ford algorithm? You have this. Let's make it for loop. So you make this first loop for 1 to n minus 1. Yeah. So you make this n minus 1 iterations of Bellman-Ford algorithm, and we just proved that if you don't have any negative cycle, then in the end, after this n minus 1 iteration, you will calculate the correct distances. So now you claim that dv is distance from S to V. So how to check if you correct negative cycles? What you can do is to apply one more iteration of this loop. So you can make n iterations of this loop instead of n minus 1. And if in the last iteration you update something in this array D, it means you have some negative cycle. So if you update some value D in the nth iteration of this for Bellman algorithm, it means there is a shortest path which contain more than n minus 1 edges, and it means you have some negative cycle. Why in power space of iteration? Yeah. What do you mean? Why the point appears in the first n minus 1 iterations? I don't get it. What I want to do? I want to apply n minus 1 iterations, yeah, like in standard Bellman-Ford algorithm. And I just proved that n minus 1 iterations is enough to calculate all the distances. So what I will try to do, I will apply one more iteration of Bellman-Ford, and if this nth iteration of Bellman-Ford algorithm updates something in array D, it means I have a negative cycle, because I have some shortest path which contain more than n minus 1 edges. That's all. So once again. So there are two ways to detect negative cycles. First way is with Floyd algorithm. Floyd algorithm, if you have a negative cycle, then at some point you will have a negative value on the diagonal of your matrix. In the Floyd-Warshall, why we get into negative in first n minus 1 iterations? No, we can get it after the last iteration. We need after each iteration to check if we don't have any negative elements on the diagonal. So after this iteration, you just check that all elements on the diagonal are zeros. If you have negative value on diagonal, it means you have a negative cycle. No, n minus 1 iteration is not enough. You need to make n iterations. In the last iteration, you may find this negative cycle. And basically, if this negative cycle contains you mean n minus 1 is always enough, because in each cycle I have a node with index at most n minus 1. Makes sense. So each cycle contains at least 2 nodes. So there is a node with index at most n minus 1. Makes sense. Yeah. So if you have negative cycle, you will find it on first n minus 1 iterations. Yeah. Yeah, good point. You may have cycle like this, n minus 1, n, and something like this. So this cycle will be founded in iteration n minus 1. So when k equals to n minus 1, then for this n, you will find this path, and the sum will be negative. Yeah. Makes sense. Okay. No, it doesn't prove anything, but nice observation. Cool. Okay, the final thing I want to discuss is some algorithm which is kind of, it's interesting, and we will use it when we will talk about minimal cost flows next semester. So yeah, what I want to do. I want to apply Dijkstra algorithm for graph with negative edges. Okay, the plan. I have some graph, and this graph contains some negative edges. So I have these weights. May be negative. What I want to do? I want to build another graph which have the same shortest paths, but the weights of all edges are non-negative. So when I will apply Dijkstra algorithm to that modified graph, and it will build me shortest paths in my graph, because my shortest paths are the same as in this graph. That's the plan. How to do it? I will assign some values to all the nodes of my graph. Some values. Secret values. And now I will modify my weights in the following way. I will say that my new weight of the edge UV will be old weight plus phi of u and minus phi of v. It's like potential function again. So I will add this difference in potentials to my weight of the edge. And what I want to do, I want to find such potentials that these new weights will be non-negative. Now, imagine you find these values. So you find some values, phi, such that if you modify your weights like this, all weights will be non-negative. Then what you can do? You can take any two nodes of your graph. Last week we used kind of the same trick when we discussed the A-star algorithm. Yeah, it's very, very similar trick. So what we'll do? we will look on some path. So we'll look at some path. So let's take path from S to T. Now, if you look at this path, let's find its weight, new weight. So what will be the weight of this path in this modified graph? So in this modified graph, the weight of this cell will be sum of all these modified weights. Yeah? What will be the sum of modified weights? It will be the sum of old weights plus the sum of differences of this potential. So you will have potential. So what you will have? You will have potential 1 minus potential 2 plus potential 2 minus potential 3 plus and so on. Yeah? So you will, for this h, you will add this difference, for this h you will find this difference, for this h you will find this difference, and so on. Now, the sum of all these differences will be the difference between first and the last one. So it will be just potential of S minus potential of T, like this. So the weight of this path will be the weight in the old graph plus the difference of these potentials. Now again, like in the previous lecture, if you modify each weight by the same constant, so this is some constant, right? So if you take any path from S to T, the weight of this path will be modified by this constant. So if you add the same constant to all weights of the path, the minimum will stay the minimum. Yeah? Again, if you have some set of integers and you add the same value to all these integers, the minimum will be increased by the same integer, right? So if you increase all the elements by the same value, the minimum will be the same, yeah? But it will be increased by this difference. Yeah? So what does it mean? It means that the shortest path is the same. So if you have some shortest path in the old graph, in new graph, you have the same shortest path. So the length of this path will be different, but the path itself will be the same. Yeah. So makes sense. Yeah? So what you will do? So if you find these values phi such that all new modified weights are non-negative, then you can apply the Dijkstra algorithm. So you apply Dijkstra algorithm for these modified weights, and this Dijkstra algorithm will find you the shortest path in your graph. So it will find the shortest path in this graph, in modified graph, but in your graph the shortest path will be the same path. That's the plan. Okay, now the only problem is how to find this potential. Well, let's draw some graph. Well, let's draw something. Something to here, and something here. I don't have this, okay. And some more, let's say. And this. Yeah, good enough. And let's apply some weights here. So let's say 1 minus 5. So I have this cycle. I want this cycle to be non-negative. So let's apply something like 4 and 3 here. So this cycle is non-negative. Now I have this cycle. I want it to be non-negative. So let's 8 here. Let's say minus 4 here and minus 1 here. Is everything non-negative? So this cycle is non-negative, this cycle is non-negative, this is non-negative, this one is non-negative, Yeah, I believe all cycles are non-negative. What? Yes. I mean, if you have these values of phi, then you can apply Dix algorithm, and it is faster than Bellman-Ford algorithm. Yeah. So you can use Dix algorithm. It will be faster than Bellman-Ford algorithm. Yeah, that's the idea. No, let's say, for example, so now I want to apply some potentials. For example, let's see. Let's say, for example, for this node, potential is 0. So I want this node, this edge would be non-negative. So for this node, I want the potential be, let's say, 4. So this edge will be 0. Now for this edge minus 5, I want this to be 4. So the weight of this edge will be minus 5 plus 4 minus this. So I want this to be, let's say, minus 2. So weight of this edge will be 1. Now for this edge, I want this potential to be at least 1. Yeah, I think that will work. So let's use these values as a potentials. So we will update the graph the following way. So let's say 2, 3. So what will be the modified weights? For this edge, the weight will be 1 plus 0 minus minus 2, so it will be 3. For this edge, it will be minus 5 plus 4 minus minus 2, so it will be 1. For this edge, it will be 8 plus minus 2 minus 4 will be 2. This edge will be 4 plus minus 2, it will be 2 minus 1, it will be 1. This edge will be 3 minus 1, 3 plus 1 minus 4 will be 0. This edge will also be 0. And this edge will be also 0. That's all. Now we have this graph. In this graph, we can find shortest paths using Dix algorithm. For example, you want to find shortest path from 1 to 4. Let's go here. I want to go from 1 to 4. The shortest path from here to here is this path. Use 3 plus 1. So this is the shortest path from 1 to 4. It's actually the only path from 1 to 4. It's not interesting. Let's find path. Let's say from 4 to 2. From 4 to 2. The shortest path is, so this path is 1, this path is 3. So the shortest path from 4 to 2 is this path. Okay. So now you can translate this path to this graph. You will have this path. And I claim this is the shortest path from 4 to 2. 2 plus 2 is 4 minus 1. Did I mess with the math? Which one is not correct? Looks fine. Okay, if I have some bug in arithmetics, I hope it's not at all fault. Okay. Now the final problem. How to find these values? So, if you have some graph with some negative edges, you want to find these values of potentials. Now we'll prove that if you don't have any negative cycles, it's always possible to find some potential function which gives you non-negative weights in the modified graph. It's always possible, but there's a trick. To find these potentials, we actually need to run Bellman-Ford algorithm. That's the boomer. Okay. Now, let's see. Let's pick some node. Let's pick some node S. There is a path. There is path from S to all other nodes. To all other nodes V. So let's pick some starting node S. Imagine you have some node such that you have path from this S to all other nodes. Then we can run Bellman-Ford algorithm and assign value phi v as distance from S to V. And now I just claim that if you apply these potentials to your graph, you will have non-negative weights in the modified graph. Now let's prove this. Let's prove that if we apply these potentials, all the weights will be non-negative. No, let's see. So, what will be the modified weights? We will be the old weight plus the difference of potential, so plus distance from S to U minus distance from S to V. Yeah. And I want to prove that this is non-negative. So I'll just transfer this to the right, and it's actually the same as distance from S to V is no more than distance from S to U plus the weight of the HV. And that's just triangle equation, right? Yeah. So this is actually true. So that's true. If I have some node such that all other nodes are reachable from this node S, then I can apply potential function as distance from S to this node. And if I use these potentials in my graph, then all the modified weights will be non-negative. It looks kind of strange, because I wanted to avoid Bellman-Ford algorithm, right? So I want to use Dijkstra algorithm instead of Bellman-Ford algorithm. But now I just run Bellman-Ford algorithm, then calculate potentials, and then modify the weights, and then apply the Dijkstra algorithm. Yeah? It looks kind of strange, right? So I try to find the shortest distance, but instead of just running the Bellman-Ford algorithm, I first run Bellman-Ford, then update the weights, and then write Dijkstra. In what case I may want to do it? It turns out there are cases when you actually want to do it like this. For example, if you want to calculate distance multiple times. So if you want to run Dijkstra several times from different nodes, so you can do it only once. So you can take your graph, run this Bellman-Ford only once, and then run Dijkstra algorithm from any node you want. And each time the Dijkstra will be run in this graph, and it will take just m log n time. For example, instead of calculate, if you want to calculate shortest path for all pairs, what you can do, you can first run Bellman-Ford, calculate potentials. Then you run Dijkstra for all nodes V. And now you will just calculate distance between every pair of the nodes. What will be the time complexity? Time complexity will be like this. So Bellman-Ford uses NM, Dijkstra uses n times one Dijkstra algorithm. Dijkstra, well, let's say if you just use the simple, if you just binary heap, it will run m log n time. or you can use Fibonacci heap and run m plus n log n time. Doesn't matter. So this will be larger than this. So total time complexity will be n log n. Or if you use Fibonacci heap, it will be n square log n plus mn. If you use Fibonacci heap, yeah. So that's slightly better than Floyd algorithm. So if the graph is sparse, so if this m is small, so if m is big, so if you have n square edges in your graph, then mn is actually the same as n square, as n cube. But if this m is small, then this algorithm actually works faster than just running Floyd algorithm. That's the whole plan. Yeah, now here, if we don't have this S, so if we don't have any node such that all other nodes are reachable from this node, what you can do? You can just add another node to your graph. So you can take your graph, add special node, and just make edge from this node to all other nodes. You can put any weights on these nodes, on these edges actually. Usually you just put zeros here, but it actually doesn't matter. Small observation. So if you don't have any negative cycles here, then in this modified graph you also don't have any negative cycles. No, since you don't have any cycle going through this node S. This node S has only outgoing edges, so you don't have any new cycles in your graph. So if you didn't have any negative cycles before, you don't have any negative cycles now. That's all. That's all. Now, again, final plan. You have your graph. You have these negative edges here. You want to get rid of all the negative edges. So you add this special node here. Add 0 edges to all the nodes. Now run the Bellman-Ford algorithm. And this Bellman-Ford algorithm will give you some values for these potentials. Now you modify your graph using these potentials. And in this new graph, you will have all the weights non-negative. So you can just run Dijkstra on this algorithm, or on this graph. And that's all. Cool. Anyone else? Did I miss anything? No, actually, in this graph, you cannot modify your graph. What you can do is just modify your Bellman-Ford algorithm. So in Bellman-Ford, we initialize array D as 0 and plus infinities for all other nodes except for S. But if you look what's going on in this graph, so in the first iteration of Bellman-Ford, you will relax all these edges. So all values D for all nodes in this graph will be zeros. So you can just modify your Bellman-Ford algorithm, so it will initialize all distances to zeros and then apply these relaxations n-1 times. It's just so if you don't want to change your graph, you can just modify your Bellman-Ford algorithm. Just start with all zeros and then apply the same relaxations. Cool. I think it's all for today.